recording. There we go. All right, so we want to use pKw to calculate the missing pH or pOH. So we need a formula that relates pH, pOH, and pKw. Does anyone know what that formula is?
pKw equals pH plus pOH.
Yeah, pKw. Why are you not writing? Ugh. pKw is equal to pH plus pOH. What does P stand for? P means to do what? Actually, that's a better way of asking it. When we see a P, what do we do with a number? P means take the negative log. And do we know what the value of KW is? 1.0 times 10 to the negative 14. If you need to use 1.00 to get enough sig figs that you're not dipping your number out of, if you're not making your number less precise. 1.00 times 10 to the negative 14. Okay, we're mostly going to use this one because this is the one that is on your data booklet. So if you look at your data booklet, where do we find KW on the data booklet? On page, go look it, go find it. It's not on the periodic table, go find it. Don't say it out loud, let everybody go find it. You're gonna point it out to your neighbor. You're gonna say, here it is. Does anybody need a pink sheet? Anybody else pink sheet? Okay. Why is this like dipping down onto the board? I don't like that. Let's make that go up a little bit higher. There we go. So point to it and show your neighbor if you have not already done so. What page are you on? You're on page 6. Excellent. And where are you? Are you near the top or near the bottom? You're near the bottom. And you can see down here, so many things written on this one. Down at the bottom, we have H2O turning into H plus and OH minus. And that gives us the value of 1.0 times 10 to the negative 14. That is KW right there. All right. And it is the KEQ for what process? It's the KEQ for there's some language here that you need to know. Autoionization. You need to know that word. Of. How did you guys do yesterday's homework and not know the word autoionization? Do you like not pay attention to what you're doing in your homework? Do you just be like, oh, I found it, autoionization. Now I'm just going to throw that out of my brain. Like, it's weird to me. If you do homework, you know what? Work on getting that homework to stay in your head. It's not just like, oh, I do it so I get it done. Work on getting those vocab words like in your head so you don't get to the end of the unit and be like, oh, dang, I don't know this, right? Next year, nobody's going to be doing this for you. You'll need to do this yourself unless you're in grade 11 and you're still here next year, in which case you'll still have people doing this for you. Okay, the autoionization of water. What's the other way to write the autoionization of water? Here we have H2O gives H plus plus OH minus. What's the other way? Yes, H2O plus H2O gives, and we have a hydrogen going from one of the waters to the other water, and a hydrogen is an H plus. Remember? What do we call that H plus? That H plus is called a proton. All right, that's a proton. So this water is giving a proton. It is donating a proton. What type of species does that make the right-hand water? This water here is a what? It just donated a proton. If it donates a proton, what do we call it? We call it a proton donor. What is the name for proton donors? Bam! That is a Bronsted-Lowry acid. Okay. What is this other water doing? It's receiving one. It is accepting a proton. It accepts a proton. Therefore, what do we call it? A Bronsted-Lowry base. Does this seem familiar from your spring break homework? Yeah. Excellent. Good. Okay, so we have our Bronsted-Lowry base, we have our Bronsted-Lowry acid, and this guy over here has grabbed a proton, so it becomes H3O plus, and the other one becomes OH minus, and its KEQ is also called what? The KEQ for this equation is called KEQ is called the process is called the autoionization of water. That's correct. Okay, so this is the autoionization of water. What does auto mean? By itself. By itself. Okay, if you're on autopilot, the plane or the car will drive itself. Yes? What does ionization mean? To turn into ions. Okay, which will be an electrolyte because an electrolyte contains ions. Okay, so we have the autoionization of water. Water ionizes with itself. What do we call the KEQ for that process? KW. Now, if we were to look at the products of this reaction, and we said, what if we're looking at the reverse reaction? Who is donating the proton in the reverse reaction? Tell your partner, who is donating the proton in the reverse reaction? So this is H3O plus, yes? Or sorry, not H3O plus. What am I saying? We get an H plus being donated. And so who is the Bronsted-Lowry acid in the reverse reaction? H3O. So that is also a Bronsted-Lowry acid. Okay? And OH minus then is accepting the proton, and it is a Bronsted-Lowry base. So on any equilibrium where you have a Bronsted-Lowry acid and base on one side, you will also have a Bronsted-Lowry base on the acid and base on the other side. Okay, so that's all about Kw, and Kw is 1.0 times 10 to the negative 14. And so now going back to our other thing here, if P means take the negative log, then pKw is equal to the negative of the log of what?
Oh, negative log of pKw, what else? pKw over pH.
No. pKw is the negative log of Kw.
Yes.
Right? Yeah? Because pH is the negative log of H. POH is the negative log of OH. So pKw is the negative log of Kw. And so that is equal to then the negative log of what value do we put in there? 1.0 times 10 to the negative 14. And that gives us 14.00. How many sig figs in 1.0 times 10 to the negative 14? 2 sig figs. How many sig figs in 14.00? Also 2 sig figs. Any p value, pKw, pH, pOH, has had a log taken. And what that means is that the number in front of the decimal is the power of 10. So it is not significant. This is the power of 10. Therefore, it's not significant. So anytime you're looking at a pH, a pOH, a pKw, only numbers after the decimal are significant. Oh my God, what am I doing? Why did it come out on my face? I have a drinking problem. What is going on? What am I doing? That's exciting. Okay, let's try that again. Successfully drank from the bottle. Okay, good, good. Life is looking up. All right. So going back to then our original question, took the long way there. We know that pKw is equal to pH plus pOH. And we know that pKw is equal to 14.00. So if we know our pH, our pOH is equal to 14.00 minus 3.78, which is equal to 10.22. And our pH is equal to 14.00 minus pOH, which is 5.19. Oh, oops, 10.22. So sorry. Is it acidic or basic? Yes, let's go into that. pH less than 7 is acidic. pH greater than 7 is basic. pOH less than 7 is basic. And pOH greater than 7 is acidic. So we look and we say, my pH is low, therefore it is acidic. It kind of almost goes opposite of what you might think, right? You're like, hydrogen, the pH is low, therefore it must be basic. But no, if the pH is low, hydrogen ion concentration is high. So it almost goes backwards of what you would think. So over here we have 5.19. We get 8.81. So that's going to be basic. Do we need to do the last two, or are we good to go? We're good to go? Okay, excellent. All right. Do we have any other questions from the homework? All right. In that case, on we move. And I think we are going to, let's see, 4.1F, which is on page 42. Okay, so we're going to do a little bit of role play here. We are going to become Bronsted-Lowry acids and bases. So everybody is going to either be a Bronsted-Lowry acid or they're going to be a Bronsted-Lowry base. So if you're sitting by yourself, you can maybe turn around and find somebody else, or you can just be like, okay, I'm going to observe my two partners, because it might be a little awkward back there. I don't know. Anywho, what you're going to do is one of you is going to have a proton. Your proton is just going to be whatever writing implement you have. Yes? And one of you is going to be holding your writing implement, and one of you is not. So one person has it, one person doesn't. Okay? Sort yourselves. There's 3 of you there. One of you can observe, or one of you can go and hang out with one of these 3 ladies in our back row there. That's also fine. Okay, and maybe you can turn around Go with Nicole or something like that. Yeah? Okay. So what we're going to do, okay, what we're going to do is whoever's the acid, hold up your pen high in the air so I can see you. Okay, if you are the acid, you're holding up your pen and you are going to donate it to the base. Give it to the base. Now, whoever was the acid now no longer has an H, yes? Are they able to take an hydrogen back? Yes, they are. Take the hydrogen back. No. Okay. Now, when they took the hydrogen back, what did they act as?
A base.
A base. Now, do it again, and we're going to focus on the base this time. Base, what did you just do? All my bases out there, what did you just do? You accepted a proton. Now you have a hydrogen on you. What have you turned into? You've turned into an acid. Act as an acid now, please. Okay? And that's why we end up with an equilibrium. And if I'm an acid, I turn into a base. And if I'm my tray is taking the place of the base for me. If I'm a base, I turn into an acid. And here I am in my acid form. You can sit down now. Thank you so much for entertaining me there. And by entertaining me, I don't mean like, ha ha ha. Anyway, I just mean, putting up with my nonsense. Yes? What do we call the two chemicals? This chemical and this chemical together. The one with the hydrogen and the one without the hydrogen. Those two are called something. I was a Bronsted-Lowry acid. I have turned into a Bronsted-Lowry base. I am a Bronsted-Lowry base, and I turn into a Bronsted-Lowry acid. What is the difference between me here and me here?
You're Bronsted-Lowry base or acid.
I either have a proton or I don't have a proton. Am I still Ms. Spence, though?
Yes.
Okay, I'm hydrogen Spence, and I'm non-hydrogen Spence. Yes? Okay, these two species here, this one and this one, that's called a conjugate acid-base pair. So if you were confused by what a conjugate acid-base pair is, it is this one and that one. Okay, so we are going to write the conjugate base for these three acids. Now, in order for a Bronsted-Lowry acid to turn into its conjugate base, it needs to lose a proton. It's going to donate a proton to somebody else. Right now, we don't know who that somebody else is. What would happen to that Bronsted-Lowry acid if it lost a proton? What would it become? Try writing those down. So HCl would become what? The H is gone, but not just the H. What else did we lose?
Proton, so it's going to be negative.
We lost a positive charge also, so it's going to become Cl minus. Try the next two on your own. Try writing the conjugate base for the next two Bronsted-Lowry acids. Oh, and don't let me forget to show you your test later. Okay. Is there anyone else who was away and didn't get to see their test yesterday? Everybody else got to see it. Okay, cool. Check with your partner, see what you got. Did you get the same thing?
But they're just still the same.
All right, I'm going to call some names here. So if you don't know, if you're like, I don't know, I feel unsure about my answer, go check with some people. Okay, HSO4 minus, Alexander, what is its conjugate base?
CO4 minus.
Except for S, but I know you meant S. You said C.
Oh, yeah.
That's okay. I know you meant S. Okay, so we get SO4, and then the charge is?
Minus 2. Oh,
Why is it 2 minus?
oh yeah, because of the loss.
Because we lost a proton, a plus charge. Okay? And HPO4 2 minus, its conjugate base is Bella. PO4 3 minus, yes. Okay, and together, these two guys here together are a conjugate acid-base pair.
All 3 of them.
Yep. Okay, these guys here together make a conjugate acid-base pair. These two guys here together make a conjugate acid-base pair. The next thing we're going to do is we're going to take Bronsted-Lowry bases. And you'll notice sometimes I get lazy or I need a little bit more space. And so instead of writing a Bronsted-Lowry base, I just write a Bronsted base. Or sometimes I'll just write a BL base. The full name, though, is Bronsted-Lowry. So we're going to start with Bronsted-Lowry bases this time, and we're going to turn them into their conjugate acids. Do you guys think you can do that? Okay, give it a try. When you are done, check with your partner or neighbor that's near you. Because again, I'm going to draw some cards and get you to tell me. Anyone need more time? We're good? Okay. Not here. Okay, Owen Campbell.
But I accidentally messed it up. I was writing his bases instead of acid.
Okay,
But
okay.
The last one
The
is
last one is?
H2CO3, I think.
Yes, the last one is H2CO3. Excellent. And you caught your mistake, so you're good to go. Excellent. All right, and let's go back up to CO3 2 minus. Zoe, what did you get for that? HCO3 minus. Yep. And the next one is really tricky. I'm going to ask for a volunteer on this one because it might be a little bit different, Alexander.
I would tell it could be either CH4COO or either like CH3COO.
Okay, let's check and see what we think of these options. Don't write them down yet. And I'm going to draw you the structure of this compound. I'm going to draw you the Lewis structure. We got a carbon with 3 bonds on it, bonding to hydrogen, hydrogen, hydrogen. That bonds to a C, which has a double bond to an O, which has a single bond to an O. And our negative charge is there on that oxygen. Maybe I should put that up top. Our negative charge is here on that oxygen. Where does the hydrogen attach? Tell your partner, where does the hydrogen attach? Does it attach to the carbon? Does it attach to the other carbon? Does it attach to the top oxygen, to the bottom oxygen? So we got a few choices. We've got the yellow carbon, we got the green carbon, we got the blue oxygen, and we've got the pink oxygen. So what does the hydrogen attach to? Do we like yellow, blue, green, or pink? We like green? You like pink? I've heard one person say green and one person say pink. Think about it for a minute. Chat with your neighbor. I feel like you need a little more processing on this.
What do you mean so is blue? How do you know it's blue?
But it can't be carbon. Let's think of that good point. Like,
I think go to the green, make it, yeah, I think no, yeah.
Now remember, that hydrogen is going to attach by a covalent bond. What is a covalent bond made of? What does this line represent? That's a single bond. What is a single bond made of? What kind of particle makes that bond?
Yeah, let's see.
What is a covalent bond? Describe it to your partner. What is a covalent bond? A covalent bond is when what happens? They share electrons. What's the bond made of? Covalent bonds is when they do what? They do what? No, we just said it. I just said it. When they do what? Share electrons. What's the bond made of? Shared electrons. Not rocket science. I'm not trying to trick you here. That covalent bond is made of two shared electrons. What you got is you got your nucleus of carbon. Oops, nucleus has a U. Yeah? That's our nucleus of carbon. We have our nucleus of hydrogen. What does that positive nucleus do to the other positive nucleus? What do positives do to positives? If I put a positive charge near another positive charge, what will they do? They will repel one another. So why are they sticking together rather than repelling each other? Because there are negatives in between. Yes? Those are our pair of electrons. And so that positive nucleus attracts. This is not part of grade 12 curriculum, but I feel like if I sent you out without knowing this to like the great wide world beyond, that would be sad. Okay, so the positive nucleus attracts the negative shared electrons. So a covalent bond is a pair of shared electrons. Yes, in between two nuclei. Now, knowing that, how is hydrogen going to bond with that molecule? We need a covalent bond between hydrogen and something. And what's a covalent bond again? A covalent bond is a pair of electrons, a pair of shared electrons. Oxygen has a pair of electrons to share. Plus, we also have a negative and we have a positive. What does positive do to negative? They attract. So who is that hydrogen going to stick onto? It's going to stick onto that oxygen. And in fact, what's going to happen is you are going to have this pair of electrons here, let's just say, and it's going to share with the hydrogen, which does not have electrons, yeah? Because that hydrogen has no electrons. So what you'll end up with then is, where can I draw this? Because I've really run myself out of room. I'm going to draw it up above. We now have H, C, H, H, C, double bond O, O. Now, instead of that last pair being just oxygens alone, it's going to be bonded to a hydrogen. Yeah? So what then would be the correct formula for CH3COO minus with an extra hydrogen? What would we write for the formula for this puppy, right? Whoa, what just happened? That was crazy. What's going to happen to that guy? What's its formula going to be? CH3COOH, because that H attaches to the last oxygen, which is why we write that in the strange format that we do. That's why we don't just write C2H4O whatever, you know, like we actually write out the whole thing. So this becomes CH3COOH. All right. And our last one we come to is HPO42 minus. What does that become as its conjugate acid? Nathan. 2PO4 minus, absolutely. Okay. And what do we call these two together? That is called you're almost right. You need to get the words in the correct order. The adjective comes first. Conjugate. And we never say base acid. We always say acid base. It wouldn't be incorrect, but it would be weird. Do you know what I mean? Yeah. Now, in all of those examples, there are two substances that can act either as an acid or a base. Go find those two substances that are acting as both an acid and a base. So you're going to look at both lists, okay, the acid list and their conjugate bases. You're going to look at the base list and their conjugate acids, and you're going to say which of those species there are both acids and bases. So you'll find it under the acid heading, but you'll also find it under a base heading.
Well, probably yeah, after the charge, also CO3, CO3, no, that the first one is like amphiprotic. Is it
Which one?
the first one?
HCl?
No, no. The CO3, HCO3 minus.
HCO3 minus?
That
I've had a suggestion of HCO3 minus. Let's focus in on that one. Here's HCO3 minus. Where else do we see HCO3 minus? Oh, look at that. It appears as both an acid and as a base. So, whoops, didn't want to do that. I wanted to do that. One of our things that can act as an acid and a base is HCO3 minus. Has anyone found the second one? Yes? Do you want to tell me? HPO4. Let's find that one. We've got HPO4 is here, and that's in our base side, and we have HPO4 here, and that's as an acid. So yes, absolutely, HPO4, not just HPO4, HPO4 2 minus. Okay, so we're going to write that one down as well. Very nice. HPO4 minus.
So anything that's like has a minus and has an H.
Yes, it has to have a minus so it can accept a proton, and it needs to have an H so it can donate a proton. And I think that actually follows down there, so I'm not going to write it anywhere else. Chemicals that can act as either an acid or a base, what are those called? What is that word? Tell your partner, say it out loud to your partner so you get used to the word. The name of a substance that can act as an acid or as a base. That's called Amphiprotic. Amphi meaning both. Protic referring to protons. So it can do both with protons. It can either donate or accept. So another definition of, practice writing the word again. Yep, practice writing it again. Say it out loud, write it again, so it becomes part of your natural vocabulary. It is a substance which can act both as a what donor and a what acceptor proton. So recognizing an amphiprotic substance, as James was saying, it has to have an hydrogen. Okay, and it needs a negative charge because that allows it to donate. And it needs a negative charge, which allows it to accept. Now there's a little bit of a qualifier on there. Any old H is not going to do it. Okay, it can't just be any old H. It has to be an acidic H. Okay? An easily removable H. So for example, if we go back to our CH3COOH, which of those 4 hydrogens are easily removable? Are all of them easily removable? No. Only this one. That is our easily removable hydrogen. When you have hydrogens attached to carbon, those are not easily removable. Okay? It has to do with, I don't know if you learned about this last year, it has to do with electronegativity. Anyone hear that word before in their lives? What is electronegativity? How good an atom is and again, this is not required for grade 12, but again, I would like to send you off into the universe kind of knowing this stuff, right? In theory, you did it in grade 11. How good an atom is at pulling bonding electrons towards itself. Okay, so in general, carbon and hydrogen have similar electronegativity. Yes? So the electronegativity of carbon is approximately equal to the electronegativity of hydrogen. I need a volunteer. Yes. Okay, so you're going to come stand up here, and I'll turn this off for a moment. I'll put that back up in just a second, okay? But I don't want to blind Owen here, okay? So, Owen, you are going to be carbon, I'm going to be hydrogen, okay? These are our shared electrons, yes? Nucleus, what charge am I? Nucleus.
Zero.
Nucleus has what charge?
Oh,
What's in the nucleus?
Oh, plus.
Positive. Protons are in the nucleus. Positive nucleus. Yeah? You are also a nucleus. You're, did I say you're carbon? Yes. Okay. Carbon nucleus. What's the charge of Owen? The nucleus.
Positive.
Positive. Because what's in the nucleus?
Positive.
Positive. What positive things are in the nucleus? Sorry? Protons. God bless. Okay. Have we not been doing this since like grade 8? Positive protons in the nucleus. The nucleus is positive. Okay. 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 What are these?
Protons. Shared bonds. Oh.
These are not protons. Protons are in the nucleus. Protons are in the nucleus. What are these? These are shared electrons. Okay. Now, we're going to share these electrons, so you grab onto them there. And carbon and hydrogen pull on electrons approximately the same. Okay? Let's not break the pens, so don't pull too hard, but a little bit harder than that. There you go. Okay? Now, is this hydrogen going to fall off easily if it's holding on to the protons with the same strength as the carbon?
Yeah.
Am I going to fall off easily? No. Okay, now, you're going to become oxygen. And oxygen's electronegativity is much, much greater than carbon and hydrogen.
How do we know that?
I'm just going to tell you that for now. I'll tell you later, okay? But anyway, so now, Owen is now oxygen. What does that mean he's good at doing? Pulling those bonding electrons towards himself. And I'm not nearly as good at it. Yes? So what can happen is Owen is pulling, and I'm trying to hold on, Wow! And look, at some point I just fell off. Maybe because there was a water and I latched onto the water and became hydronia. Yes? Or maybe there was another thing around. Anyway, thank you so much. That was fantastic. Little bonus mark for Owen on your next quiz. I know you volunteered and you're like sad now, but it's okay. You got your bonus earlier this year, so you're good. Okay. Oh, I need to turn this on again. There we go. Carbon and hydrogen are approximately equal. And then we have the three big electronegativities are nitrogen and oxygen and fluorine. You don't need to know this for grade 12, okay? You don't. But chin off, if that's helpful for you later in your life. This is our strength of electronegativity. There is a table. Basically, the further right you go on the periodic table, the more electronegative it becomes. The further up you go on the periodic table, the more electronegative it becomes. So if we look on our periodic table, who is the furthest up and to the right? Helium, except that the noble gases do not do what? They do not. They don't bond, right? So there's nothing to do with bonding electrons for them. So it's going to be fluorine is the most. And then because we're still in the top row, oxygen second, nitrogen's third. Okay. And you really don't need to know anything more than that. You just need to know that carbon is less than those three, significantly less than those three. And then hydrogen, because it's positioned so strangely, it's really hard to say. But if you kind of remember that hydrogen and carbon are kind of the same-ish, then you're good to go. Okay? But like I said, you don't really need to know that for grade 12 chemistry. What you do need to know is that if we have a structure like this one here, who is the hydrogen that's going to fall off? The hydrogen's attached to the carbon or the hydrogen attached to the oxygen? The hydrogen attached to the oxygen, and the other ones will just stay there. Or you can just memorize it. Or you don't even have to memorize it. You can look on your data booklet and be like, what the heck? Which one comes off? And you can say, where is my acetic acid, my ethanoic acid? Oh, there it is in green. Okay. And you can say, which hydrogen comes off? It's the one that's attached to the oxygen. That's the one that comes off. All right, so you don't actually have to memorize it. You don't actually have to even understand it. But is it kind of nice to have that background in your pocket? Probably. Okay. All right. My God, we've spent the whole class. And how much have we covered? Nothing. Half a page. Woo! Okay. So you have to have a hydrogen to be amphiprotic, so you can give away a hydrogen. You have to have a negative charge, so you can give it away. There is an exception. Water is amphiprotic, but it lacks a negative charge. So you just need to know that water is amphiprotic. Okay? So either you need that hydrogen and negative charge, or you need to be water. And if that's the case, then you are amphiprotic. I wonder if I have my second exception to that rule on the next page. Let's find out. If not, we'll come back here and we'll put our second exception. Nope. So we're going to put it up here, our second exception, and it's an exception in the other way, okay? It's something that has a hydrogen and it has a negative charge, but it is not amphiprotic.
The hydrogen.
It has a negative charge. Hydronium has a positive charge. And I would like you to go take a look on page 6 of your data booklet. Okay, go take a look on page 6 of your data booklet. And I didn't bother writing protic because I got lazy. See if you can find something that has a hydrogen, has a negative charge, but is not amphiprotic. It is not able to act as both an acid or a base. This is tricky. You could start by finding a bunch of things that are able to act as acids and bases. Let's go find some negative things. Most of our negative things we're going to find on the right-hand side. Okay, some of them will then also occur on the left-hand side. Do any of these guys here meet the criteria? Those are all my negative things up in the strong acids. Do any of those guys have a hydrogen and have a negative charge?
No.
Which one? HSO4. Okay. Okay. Let's find another one. What's our next one down the list after the gray zone that is both, that has both a hydrogen and a negative charge? We've got HC2O4. And we have, what's our next one? Let's just do one more. HSO3. Okay, so we got that one there. Oh, I'll make it a different color. Okay. Pink. There we go. So we have HSO4 minus. Does HSO4 minus also appear on the left-hand side? Here, it appears as a base. Does it also appear as an acid? Yes, here it is as an acid.
Excellent. But no, at the bottom.
Oh, whoops. Sorry. The next one down. Whoopsie. There we go. That's better. Now let's go further down our list and find HC2O4 acting as an acid. Where is our HC2O4? Give me HC2O4's Ka value. You're looking for HC2O4, but you're looking for it on the left-hand side. Once you find it, you can look up its Ka value. So we're looking for the blue one, but on the left-hand side. Yeah, okay, so we've got it down here, HC2O4, and it is at 6.4 times 10 to the negative 5. Okay. Let's go find HSO3, the pink one on the other side. Where is HSO3? On the left-hand side. Yeah, we got 1.0 times 10 to the negative 7. Okay, so here's our HSO3. Now, out of those ones, let me get rid of the ones that aren't amphiprotic. So we've got our base, we've got HSO4, base form, acid form. We've got our HC2O4, we've got our base form, we've got our acid acting as an acid, we've got HSO3 acting as a base, we've got it acting as an acid. One of those three is our exception to the rule. It cannot act in an amphiprotic manner. It can only do one of the two things. It can either only act as an acid or only act as a base. I'm not going to tell you which one. Which of those three is not amphiprotic and why? Okay.
I actually think it's actually HCO4. Because like it's actually like a very yeah, it's too weak to active base.
You said HCO4 again. HSO4. Have a chat with your neighbor. Which one of those three? HSO4, HC2O4, HSO3. Which of those three?
I have the HSO3 because I put it onto my notes.
Which one is not amphiprotic and why?
I know now. I actually have a good explanation now.
If you have a good explanation, explain it to your neighbor. That's okay. Wake him up. Tell him your explanation. Say, oh, and I have important news for you.
Important news for you. So so I think it's HC2O4 because it's attached to a carbon. It's attached to a carbon. So they're pulling against each other like equally. If you're pulling equally, they can't detach. Oh my god, that feels so hard saying that.
Except that there's a problem. That H is actually attached to one of the O's in that compound.
Oh, actually,
I'm so sorry.
Oh yeah, there's like a C on top and bottom, and there's an H on the side.
What we would have is we would have a C. Oh.
Never mind.
Like that, yeah. But you were like so on the right track. No, you are smart. You just don't know as much chemistry as I do, and which is fair because you haven't been in this world nearly as long as I have and have studied chemistry for a teeny fraction of the time that I've studied it. So, you know. So you would have an H here and an H here. Anyone want to give it a try? Yeah. Yeah, it is HSO4 because it is too weak of a base to accept a proton. Because if you look, this arrow is a one-way arrow. So HSO4 is too weak of a base to accept a proton.
Isn't that arrow but if it goes that means it's a acid.
That means that H2SO4 is an acid. It's a strong acid. Its conjugate base, HSO4 minus, is too weak of a base to act as a base. Okay? It is a conjugate base, but it cannot act as a base. That's one of the language things that's a little bit tricky in this section, is that HSO4 is a conjugate base, but it's so weak it cannot actually act as a base. So it is a base, but it's not a base. Do you know what I mean? Like technically it is a conjugate base, but it's too weak to be a base. So it's a base, but not a base. Irritating, I know. Okay, there we are. What can we do?
So do we count that as a base or not a base?
It is a conjugate base of H2SO4, but it is unable to act as a base. It is unable to accept a proton. Okay? Yes. All right. Now, I would like you guys to finish off what we didn't finish last day. This will take you through, this will get you through all that pH stuff. We'll finish this off. Where was it? We went to page 81. Today you're going to do pages 82 and 83. And you'll be so sick of pH and pOH and all that stuff by the time you're done this. You'll be like, oh my gosh, make it end. But lots of practice is good. Hi. You got homework to show me. Fantastic. Okay. Wonderful. That's your Hebden. Wonderful.
That's
We
pretty
got
cool.
this stuff here. And we go here. And we go here. Yay, thank you so much. And let's get your test for you.
Don't want to do this any.
All right.
I just want to play on my Rubik's Cube keys.
Oh, we are. Excellent. Thank you guys so much. I will see you tomorrow.
I might need to
Yay.
review how to draw
Good,
Lewis
good.
to be honest. I forgot how to draw Lewis.
Yes.
Get the
Thank you very much.
Now this is the